Professor,
Good afternoon.
good afternoon. I have a question.
Sure, go ahead.
Is this lecture going to be uploaded with the lab?
Yes.
Excuse me?
Is this lecture going to be uploaded with the lab?
Yes,
Okay, because I might need to leave soon for a personal matter, so
that's
just
okay. You can watch the lecture afterwards and do the lab, on your own.
okay. Thank you.
No, you're welcome. I believe everyone is in. Um, Plan for today is for me to lecture um for about an hour, hour and 10 minutes. Um, and then Tariq will lead the second lab module. Today will be the last day that I will cover lecture 8. Whatever we don't cover, we just don't cover. Oh, what didn't I post? I thought I did. I really didn't post it. Take a look. I uploaded it. If it didn't make it on, it means there was something wrong with the processing. Oh, it's still processing. I wonder why. Uh, okay, that's very weird. Okay, I have an idea. I have an idea that's gonna fix all your problems. Let me give you a link just from Dropbox to the Monday lecture. I don't know. I uploaded it to YouTube. It's still processing. I've never seen it take this long. Um, but it says it has 5 views, so I don't understand. Let me take a look.
Did you publish?
Excuse me?
Did you publish the video, Professor?
Yeah, I published. It's no, there's something wrong with it. It's very high def. It's so weird. Like Zoom's recordings from that day came super high resolution. Let me see. Last you guys won April 26th. So let me copy them in the chat. Oh, I did. So they are there. Okay, anyhow, in case you didn't get it, only the best quality. It's funny. Um, okay. Um, yeah, so if you can either get it on the YouTube, I don't know why it still says processing HD version. I don't really know why it gave me such a high definition. It's like 1920 by 3000 or something. Anyhow, it's there. Um, and I don't know if the TAs are on, but we can be pretty liberal. I mean, we can be generous with the amount of time we give the students to submit the lab reports. The lab for me, the only thing that I care about for the lab report is that it demonstrates that you carried out the lab and you carry out the required steps and that you made the required measurements, you obtain the correct values, just so document your work. I don't actually want like a chemistry lab report or anything like that with like I don't want a chemistry lab report where you like write out a hypothesis and narrative of everything that went down. I don't care about any of that. The only thing I care about is that you acquire some experience in making measurements of voltage or current. You know how to use the DAC cards, etc. So that's for me. It's up to I've given the TAs a lot of freedom here, perhaps too much. Maybe I've made them do too much work. Yeah, so we can be liberal with how long you guys have to submit the lab reports. But the only thing that I care about personally is just proof that you actually made them, you wired up the breadboard yourself. You made the measurements, and the measurements are consistent with what you would expect given the values of the sources and the resistance values.
Yep. Jacek, so we made it so that all labs are due on the last day of classes in one
Perfect.
PDF.
Perfect.
Sam is now yeah, Ahmed, you can contact us directly through email to
Yeah.
to troubleshoot the breadboard.
Let me just post the YouTube link for that. Yeah. If somebody can click on that link and tell me if it works for them, that would be really awesome. This lecture is brought to you by San Pellegrino Blood Orange flavor. It's called reverse advertising. No way, man. Clementine's all right. They may not like that video. You guys are probably too young for this, but there was a show. I never watched this, just straight up. Want to get that out in the open. It's called Jersey Shore, and there was a character in there. Her name was Snooki. And because of her reputation, I believe that the makers of certain purses were paying her money not to carry their purses around. So that's really reverse advertising. So maybe San Pellegrino Blood Orange flavor will tell me to stop drinking their product during these lectures. I'm not sure. Maybe it'll be the opposite. Maybe I've just now increased the sales of San Pellegrino Blood Orange 8% juice or something like that by 20 or 29 participants. Very refreshing on a hot New York summer's day. All right. Unfortunately, I have to interrupt with some educational content. Cafe One does sell San Pellegrino. Please tell Susan I say hello. Do miss Cafe One. All right. We are doing this problem. We will continue doing it. I think my plan for today is just to do 3 problems. And believe it or not, that should take up the whole hour just because of how intense these problems are. Let me actually, just to give myself some more space. I hope everyone had a great weekend. Hope the last part of your semester is not killing you. Did I not post a YouTube channel link? I did. Does it now work or something?
No, you didn't.
That's so weird. It's in my chat window. Okay, let me try again. Oh, in waiting room. Everyone, I see. I'm sorry. I accidentally posted it to everyone in the meeting room. Okay, tell me now if you see it. Okay. And it actually works? Okay. Awesome. Problem solved. Close the books on this one. All right. First thing with these this is an example of a series RLC circuit, because when the switch goes from position A to position B, what you have is a series RLC circuit, and you have a battery energizing it, so you know it's a step response. Why is it a step response? Because there's no input until time 0, and after time 0, we have a fixed input. So that's the definition of a step response. So it's a response to a step function input. So let's now analyze the circuit at t equals 0 minus. Okay. So as always, let's draw the circuit, what it looks like before that switch switches from position A to position B. Right? So we have our battery. So basically before time 0, we have everything, we have all of this, and everything out here is not alive, because there's no the circuit on the right doesn't have a complete path for the current to flow. So we have this, and I'm just going to draw the open circuit capacitor over here. I'm redoing, I know I did some of these steps last class, but I just want to redo it because there's no way that most of you actually remember it. All right, so this is 1, this is 2. This is an open circuit capacitor. It's open circuited because it has been sitting there for a very long time, since the beginning of the universe, without a change. And so in this picture, what is the value of V? This is 1 ohm, this is 2 ohms. Pardon the, oh, we have an answer from the population. 8. Sounds correct to me. That's excellent. Excellent work, Christian. 8 is correct because of voltage division, right? So this is why I said you got to make sure you have the fundamentals down. You got to be able to look at the circuit and immediately identify you have 12 volts that's divided into this load and this load. So this is 2/3 of the load here. So I'm just gonna let Sam in. So the 2 ohm resistor is 2/3 of the 12 volts, so it has a drop of 8 volts. And we also want to know the initial current through the capacitor, right? It's through the inductor. We always solve for the capacitor voltage and the inductor current. So what is the initial inductor current in this problem? I'm just gonna say, yeah, well, let's see. 0, 0, very good. Thank you guys. I really appreciate the student participation on this part of the lecture, where historically things have been very quiet, and that makes me sad. Okay. Okay. So these two these are the initial conditions of the capacitor voltage and the inductor current. All right, let's draw this picture now at time equals 0 plus. Do my best. So at time equals 0 plus, we're gonna have our RLC circuit. Okay, so this is our V. We're gonna just say that I is going through the, not even sure we need the I, but, and then this is 10 ohms. This is 10 volts. Okay. No, I'm not going to label the capacitance values here just to save time. So the important thing is this. You need to identify that this is a series RLC circuit. So we know we need to identify the alpha and the omega. So to get those, we need to apply the formulas. So alpha is equal to, for series RLCs, R over 2L for a series RLC circuit. So R is 10 and L is 2.5. So it's 10 over 2 times 5 is equal to 2. And omega naught is always 1 over the square root of L times C. So 1 over the square root of 2.5 over 40. So that's going to equal to the square. It's going to be 2.5 over 40 is 1 over 16. A square root of 1 over 16 is 1 over 4. So 1 over 4 is 4. Okay, so this is one of these cases where the alpha is smaller than the omega. Change the 5 on top to 2.5. Did I make a mistake here?
Where it says 10 divided by 2, oh, you put 2 times 5. Should be 2 times 2.5.
Oh, thank you. Thank you. That's very astute. Yeah. Let me see if I can use my eraser. Oh, all right. It's okay. I'll just write it out. Then omega. Very frustrating with the Zooms. One over square root of L times C is equal to 1 over square root of 2.5 over 40 is equal to 4. So this is underdamped series RLC. So we know that the general form of our overall solution is going to be equal to Vn of t plus Vf of t. So in this equation, Vn is called the natural response. And I'll define that in just a second. And V of F is the forced response, which is the contribution to the battery. Okay, so natural response is as we saw with the source-free circuit. So it's going to be equal to exponential negative alpha times t times A1 cosine. I'm just going to call plus A2 sine. Okay, so it's a little bit. So that's the equation for the natural response. Now, the omega d here, which I'll define, squared minus alpha squared. And that's going to be equal to square root of squared is equal to, so 16, so square root of 12. I'm gonna run out of room here. Okay. So let me see if I can figure out how to get some more room on my screen here. Right, so what is omega d? Where omega d is just, it's the frequency of the oscillatory part of the natural response. So that for an underdamped response, the transient is composed of a sinusoid with an amplitude that is decaying exponentially. So the time, the coefficient on the exponent is equal to alpha, which is, or negative alpha, which here is equal to -2. And then the omega d is just by definition the square root of omega naught squared minus alpha squared. So all these equations, for those of you that, maybe I won't show them now just because I have the overlay. Okay. Right. So far we've defined our overall response, which is composed of the sum of the natural response, which we still need to solve for the coefficients for, and the forced response. So the forced response is easy. It's just equal to the battery. So that part, so the forced response is just, it's just a matter of knowing what that voltage is going to be at time equals to infinity, which in this case is going to be equal to 10 volts. So I think now what we're going to do, I'm going to copy over this slide and let's see, I'm going to erase a bunch of this. And let's see, I want to keep this, but I want to just see if I can move this. See if I can move the drawing. No, okay. Okay, maybe what I'll do is, let's see. I'm actually going to erase the circuit for now. These questions, when I did them live, all right, forget it. When I did them live, it was like a 3 chalkboard event. So not really surprised that I'm having issues finding room here. Okay, so what do we have and what do we need? We have V of infinity. We have alpha. I'm just going to write down alpha is equal to 2. And omega d is equal to square root of 12, which is equals to, I'm just going to approximate it by 3.46. Let me just see if I can move this over. Move this over here. Okay. All right, good enough. So we need to somehow come up with, and maybe I'll fill it in. And getting the natural response is most of the work. So the natural response is going to be -2 times t, because alpha is equal to 2. And then it's going to be times A1, whose value we don't know yet, plus A2 sine 3.46t. All right. And so now we can write our full response. That's our, now we have the full expression. This is everything we have in this in this last line here. So we have the sum of the forced response, which is 10 volts, and this transient natural response. And what we need to do now is use our initial conditions all the way back from the beginning. So we had initially, we had V naught was equal to 8 volts. And we also are going to need an expression for V prime naught, which we don't have yet. So let's actually tackle this. Let's try to come up with an initial expression for V prime naught. And to do that, let's draw again. Let's draw the series RLC circuit. And for the natural response, we can actually just omit the battery. Which isn't really that important here, because the key thing here is that we want to relate the inductor current with the capacitor voltage. So now at time 0, I of 0 is equal to 0. And the reason is because of continuity. So before this switch flipped from position A to position B, there was no current through this inductor. Hopefully everyone sees that, because there was not a complete path for the current to flow on the right part of the circuit. Now, the moment that switch flips from position A to position B, the current to the inductor is still going to be 0, right? So because of continuity. And the key thing here is that CV prime of 0 is equal to I of 0. Because these two elements, the inductor and the capacitor, are in series when the switch is in position B. And so we have this very important relationship between the inductor current at time 0 and the derivative of the capacitor voltage at time 0. Right. Oops. Oh, come on. So finicky. So write that again. So we have I0 is equal to 0, which means that what I'm trying to get at here is that the initial derivative of the capacitor voltage has to be 0, because it's proportional to the inductor current, which is 0. So now we have an initial condition for the capacitor voltage and its derivative, which is all we need. Because now notice that we have 2 coefficients, and so we just need 2 equations, and we have those 2 equations. And so now is where I'm going to evaluate this full solution at time 0. So here's where I'll ask for you for help. What is V of 0 going to look like? Who can tell me what's going to be the form of this solution when time is equal to 0?
A1 plus 10.
Excellent. Yeah, A1 plus 10 is absolutely right. And that has to equal to 8 volts, which means that A1 is equal to what?
-2.
-2. Exactly, right? And the other thing that we can do is we can actually differentiate this function with respect to time and set it to 0. And I'm just, because of the time constraints, what I'm going to do is I'm going to spare you of the derivative. I'm just going to evaluate a derivative at time equals 0. And it's not hard. You just use the product rule to differentiate the product of the exponential and the sinusoid. And what you're going to be left with is -2. You may be able to see this actually. A2. And that has to equal to 0, right? So if you take the derivative of this function and set it to 0, you will be left with -2a1 plus 3.46a2. And the reason is that the derivative of a cos is a sine, and the sine of 0 is 0, and then derivative of the sine is a cos, and which is where you get this term. And so what you end up with is that A2 is equal to -1.156. Okay. So now we have both our coefficients, which means that we have everything that we need to write down the full solution. So the full solution is going to be exponential minus 2t. Oops, there's a typo here. It should just be 1t. Then A1 is equal to -2 times cos 3.46t minus 1.156 times sine 3.46t plus 10. And so this solution is for the capacitor voltage V here. And meaning that when time goes to infinity, all that you're left with is a 10 volt from the battery. Okay, so we are also asked to find VR of t. So what I'm going to do now is I'm going to draw, I'll try to do a better job of drawing the circuit after time 0. And I'm going to ask you guys for help with, so assuming that the switch is going to be in position B, so we have a solution for V, and we want a solution for VR in this circuit, where VR is the voltage drop across a 10 ohm resistor. So my question to you is, and this does not require too much algebra at all. How do I translate this voltage into this voltage? All right, so I'll start you off. I'll say VR of t is equal to I times 10, where I is the current through this resistor. Notice this is a series circuit.
If that's the case, wouldn't it be 0 then?
Be 0? Oh, no. I'll give you guys a hint. The capacitor and the resistor are in series, which means that they are always guaranteed to carry the same current by definition. In other words, this I here applies, oh, we have a, yes, Christian, excellent. Exactly. Sorry, the chat window is being, let me just move the chat window. Yes, exactly. That's excellent work. So we can just now, the I here is just CV prime. CV prime. And so basically, I'm not going to do the work, just I'm not going to do the manipulation, but if you take this, the solution for V, you take its derivative, multiply it by the capacitance, and multiply by 10, then you get the solution for V of R. And I'm just going to write it down here. You know, I'm going to post the solutions that have all the steps. Oh. Can you guys still hear me?
Yeah, but like you are like we cannot see your face or your screen any longer.
Okay. Can you see my screen at least?
Yes.
Okay. All right. I don't know what happened there. I think Sam Pellegrino may have heard that I was your first advertising. Anyhow, see if I can finish this off. So we have an expression for V of t, which is 10 plus exponential minus 2t times negative 1.156 sine of 3.46 t minus 2 times cos 3.46 t. So that's my expression for V of t. And now what I'm saying is that VR of t is equal to I of t sorry, I just had to let someone into the chat room, into the Zoom. Oh, give me a break. Okay, so VR of t is equal to I of t times 10. And I of t is equal to C times V prime of t. So then when you differentiate this solution for the capacitor voltage, multiply by the capacitance, and then multiply by 10, you get that VR of t. Unfortunately, do not have the time to work through the arithmetic with you in class. But again, as I was about to say, all the solutions, the full solutions, I'm going to post to Blackboard, you know, PDFs of my handwritten solutions. So this ends up being a solution for V of R. So again, all I did here is I just use the fact that this capacitor and this resistor are in series when the switch is in position B. And so all I had to do, once I had the solution for the capacitor voltage, I was able to convert it to the current, right? Because the current through a capacitor is equal to the capacitance times the derivative of the voltage. And then I multiply that by the resistance of 10, that's Ohm's law, to get my final solution. All right. I have about half an hour. So we did this problem. Okay. A little bit of theory, a very short amount of theory. The last, remember I said that there are 4 types of circuits that we consider here. We have source-free RLC, source-free series RLC, source-free parallel RLC, step response series RLC, and step response parallel RLC. So we're on the last one here, and it's virtually identical to the series RLC with a few exceptions. So notice here we have a current source that is disconnected from this RLC circuit up to time 0. So when this is an open circuit, when this is a short circuit, when the switch is closed, the current just flows like this. And it bypasses the parallel R, L, and C. So again, it's really important to understand that when this switch is closed, this entire current just flows through this mesh. Now, as soon as that switch opens, this current is all of a sudden going to invade the RLC. And we are interested in how much current goes through the resistor, how much current goes through the inductor, and how much goes through the capacitor. Okay. And to do that, we apply, as I'm sure many of you guessed, we apply KCL. Right, so this IS gets broken up into 2 parts. The current through the resistor, which is equal to V over R, the current through the inductor, which we just defined to be equal to I, and the current through the capacitor, which is equal to C times dV over dt. And we also have, by definition, the voltage across an inductor is equal to the inductance times the derivative of its current. And so now we can plug this in to here and here. So notice we have a derivative, and then we're going to plug in another derivative into it. So we're going to have a derivative of a derivative, and that's what's going to give us the second order differential equation, where you can identify that the alpha is going to be equal to 1 over 2 RC, and the omega is going to be 1 over root LC. Same thing as before. So in series RLC, we were solving for the capacitor voltage. In a parallel RLC step response, we're solving for the inductor current. So you either have to memorize that, the fact that I just stated, or you just have to be able to derive this equation. And from this equation, you can get the characteristic polynomial for I. And as before, our complete solution is going to have 2 parts. It's going to have a natural response, which is a transient term, and the forced response, which is always on. And the forced response, as you probably may have guessed, is just equal to I of S. So the forced response is always going to be a constant. Okay, and so as before, we have our 3 cases. We have the overdamped case, where alpha is bigger than omega. We have the critically damped case, where alpha is equal to omega, and the underdamped case when alpha is less than omega. So the only difference between this and the source-free version is the presence of this forced term, which is equal to I of S. And our job here is to solve for the constants A1 and A2. And we get those constants from the initial conditions. So we're gonna always have to derive an initial condition for I and an initial condition for its derivative. And as before, you solve for the inductor current all the way through to the end. And once you have an expression for the inductor current, you can use it to solve for the other elements in the circuit, such as the resistor current or the capacitor current. And so basically, kind of the recipe that we're using for second order circuits and first order also actually, is that our solution is always going to be a linear combination of a steady state term and a transient natural response. So I'm gonna skip the example because of time, and I don't find that these the slideshow problems work very well in the lecture. Whereas they work a little bit better when I actually do them step by step, which is what I'm going to do. And this is one of my favorite problems because it doesn't require a lot of math at all, but it does require you to think. So what is missing from the circuit?
Resistor.
Exactly. So the question I always ask at this slide is, we've been learning how to attack RLC circuits, but here we have an LC circuit. So how can I fit this problem into the RLC framework?
Would the R be infinity at this point?
Ah, yes, very well done, man. Very well done. It is infinite. Most people say 0 here. Which I will not have blamed if anyone said 0, but yeah, it actually is infinity. Because if you were to draw a resistor here, right? If you were to draw a resistor and give it a value of R, right? What value of R would make the circuit not change because of its presence, right? It has to be infinity. If it was 0, then this is an open, then this would be a short circuit, and all of this current would flow through the resistor. So it can be 0. So it does have to be infinity. So in other words, an open circuit is equivalent to an infinite resistance. And so now we know that our alpha is equal to 1/2. See, so what's alpha going to be here? Audience answers 0. Excellent. Alpha is equal to 0, which is so when alpha is equal to 0, what that signifies is that we do not have an exponential decay. So remember, well, actually, I'll wait before. And then we have omega naught 1/square root of L times C. You should be able to tell that L times C here is equal to 1. So omega naught is going to equal to 1. So is this our alpha is 0 and our omega is 1? So can anyone tell me whether this is an overdamped, critically damped, or underdamped circuit? Okay, so when alpha is less than omega, the solution is underdamped, which means that our natural response for V is going to have an oscillation. Times here omega d conveniently works out to be equal to 1. And so our Vn of t is going to have a really nice looking form. It's going to have so our natural response here just consists of a cosine and a sine term, because our omega d is equal to 1 and our alpha is equal to 0. So the exponential terms drops out. It simplifies to 1. And the frequency, the angular frequency of our sinusoid is just 1, which makes this really nice to work with. Okay, one thing that we haven't done yet is the initial conditions. So who can tell me what is the initial value of V0 here?
Would it be 0?
Yeah, it has to be 0, because this, if I draw this circuit at time equals 0, I just have, it's just, actually, it's just, erase this. It's actually just the open circuited capacitor. This is V. And this is I. So this is what the circuit looks like at t equals 0 minus, right? You just have an open circuited capacitor. The reason that I haven't drawn the current source is because it turns on, it's a step function source. And so it turns on after time 0. And so we also know then that our initial inductor current is equal to 0, is equal to the derivative, is equal to C times the derivative of V. And therefore, the initial capacitor voltage derivative is equal to 0 volts per second, because the initial inductor current is equal to 0. Okay. And this applies to just this little circuit here, where all there is the capacitor and the inductor, because the current source has not yet turned on. Okay. So now what we have to do is write the full solution. We also need, the full solution. So maybe before I write the full solution, let's draw the circuit at time equals to infinity. So at time equals to infinity, we have our 20 amp source. We have our open circuited capacitor. It's fully charged at this point. We have our short circuited inductor. So who can tell me the final value of the inductor current here? In this picture. So we have a 20 amp battery in parallel with Yeah. 20 is right. Very well done. Okay. Text. And B. I also know that V of infinity. V of infinity is going to be equal to 0 volts. And the reason is in this picture, the capacitor is in parallel with a short circuit. So this is an example. We have a 20 amps currents flowing around the outside. And therefore, the voltage difference between this point and this point is 0 volts. Okay. So let's now solve for let's write the full solution for V of t. V of t is equal to Vn of t plus Vf of t. So in this case, Vn of t is A1 cos t plus A2 sine t plus 0. Do this. A1 cos t plus A2 sine t. There we go. Okay, so we just need our first initial condition is that V at time 0 has to equal to 0. Okay, so what that means is V of 0 is equal to A1 is just equal to A1 because cosine of 0 is 1 and sine of 0 is 0. Therefore, we know that A1 has to equal to 0. And then the second step is to take the derivative of this function and evaluate it at 0. So we have the derivative of t is going to be equal to negative A1 sine t plus A2 cos t. And that has to equal to 0, which means that let's see, that is something wrong here. So I actually just realized that the whole thing I've been solving for V when the solution that I did before class was for I. And so I think what I'm going to do is, I apologize for this. Everything is good except, oops, didn't want to do that. Okay. Let me just start from here. So omega naught is equal to 1 over square root of L times C is equal to 1. And so what I wrote the solutions for V and I should have written them for I. So that the form is the same. And I of NT is equal to A1 cosine T plus A2 sine T, and I of FT is equal to 20. Okay, and so basically we're doing the same thing, except that for a parallel RLC, the solution that we want to obtain for is for the inductor current, not the capacitor voltage I just did before this. And I apologize for the confusion. So we have, this is our overall solution. So we need the initial conditions for I of t and I prime of t. So again, we have that, just going back to the I of 0 is equal to 0 amps as before. And I prime of 0 is also equal to 0 amps per second. The big difference is the force response here is 20, right? So as we drew in this picture, the I of infinity is equal to 20. I think you guys got, I think that was answered in the chat. And so let's write now our full solution for I of t. Plus 20. And now what we're going to do is we're going to substitute these values into this equation. Okay. So for example, I of 0 becomes A of 1 plus 20. And this is where I made the mistake here. So if that has to equal to, if A1 plus 20 has to equal to 0, then A of 1 has to equal to minus 20. Okay. And I prime of t is equal to negative A1 sine of t plus A2 cos of t. And if you evaluate that at 0, it becomes equal to A2. And that has to equal to 0. So we have the value for our A2 coefficient and our A1 coefficient. So putting all of that together, we get that I of t is equal to negative 20 cosine of t plus 20. And you can factor out the 20 and get that, which is the solution for I of t. Okay, so apologize for the detour. Basically, the key components of this solution are the following. The R is equal to infinity because an open circuit is effectively equal to an infinite resistance. And so you get your alpha and your omega. You write your complete response as the sum of the natural and the forced responses. The forced response is equal to 20. You derive your initial conditions for I and its derivative, and they're both equal to 0. And you use those initial conditions to get the values of the two coefficients A1 and A2. And so you get it. What this solution basically means is that at t is equal to 0, the current is 0. And that current basically goes up and down infinitely, right? So this is a purely oscillating, and maybe you see it better over here. That basically the solution to this problem is a sinusoid with an offset of 20. And so the inductor current oscillates between a value of 0 and 40, I believe. So what's happening in this circuit is that the energy is being exchanged, is being alternated between the inductor and the capacitor. So as soon as this current source turns on, all of a sudden, energy starts being transferred between these two storage elements. Okay, the last thing that I'm going to say on this problem is that the capacitor here is in parallel with the inductor, which means that they have the same voltage. So the capacitor voltage at all times is equal to the inductor voltage. And so if we know the capacitor, if we know the inductor voltage, we can get the capacitor voltage. But we also know that the inductor voltage is equal to the inductance times the derivative of the current. So L is equal to 5, and then times d over dt of, let's write this, 20 minus 20 cos t. And that becomes 5 times negative 20 times negative 1 times sine of t is equal to 100 sine of t. Give me a second, just have to let someone in. Okay. So we've basically, I said I wasn't going to cover any more lecture right after today, but I'm going to have to cover a little bit more next class. Unfortunately, not too much more probably. I did want to do at least one problem from the general second order circuits section. I'll just preview that section. Basically, we've shown you how to solve series RLC and parallel RLC circuits. But what happens if you encounter a circuit that doesn't fit into either one of those molds? So there's a recipe that we give you for that kind of problem as well. And it's the same things that we've been doing now. You get your initial conditions, you get your natural response, forced response, and you put them together. So probably what I'll do is spend the first half hour of Wednesday's class talking about that. We'll do one problem, and then we'll move on to lecture number 9. I'm gonna post all the solutions to all the practice problems lecture 8 right now. And I'm going to make, Tariq, you're gonna run the lab, correct? I hope. So anyways, I've made Tariq the host, and I'm gonna make Sam the co-host just in case. And
Actually, I'm not sure if Dr. Domojowski talked about like the exam. So I was grading your like question 13, and some of you try to use the mesh analysis to like calculate the value. And like as directed by Dr. Domojowski, I don't know how much extra partial credit I should give you if you got the incorrect answer. So in that case, if you receive like 0 on that question, and you thought like you was doing some step partially right, you should contact either me or Dr. Domojowski.
contact me. Yeah. I'm
Yeah.
gonna spare you of that
Yeah.
that burden. Let me deal with those.
Okay.
So yeah, no, Sam, right. I'll have to take a close look at them. So with the exams, my philosophy is to maximize objectivity of the grading. And so the way I do that, in my attempt to do that, is to basically, before I even look at any of the exams, I write down what I need to see for every point. And then, I grade it strictly based on that. And so that may lead to some exams being graded too harshly, especially if you took an unconventional approach. I'm more than happy to, if you feel like, you were graded unfairly, by all means, the best way to do it is to just send me an email and send me an explanation of why you believe you deserve more credit, and I'll be happy to take a look at those. But don't blame the TAs. I gave them explicit
I get
instructions.
0 to like lots of you, so
Okay. Yeah, so I'll probably get a lot of emails and that's okay. I mean, I guess the question is for those, Sam, for those that did mesh analysis for that problem, so that only, it doesn't apply for the RTH, like the RTH, it has nothing to do with mesh analysis, right? So it's just combining resistances. It does apply, however,
to calculate the
to
voltage. Yeah.
the voltage. And so the question is,
Like some of them got like the kind of the RTA wrong, but like the mesh analysis kind of makes sense, but I don't know how much partial credit to give them.
yeah,
Like,
that's
yeah.
tough. I guess what I'll say is, when they did the mesh analysis, like, did they have equivalent currents flowing down those? Because I believe that the solution that
Yeah,
problem was that,
the kind of what they show was like decent, but like the result, like the apply, like the equivalent circuit was kind of wrong. So like the circuit was not correctly, but the way they set up it based on the equivalent circuits were correct.
okay,
Yeah.
okay, you can enter the grade, Sam, as is, and let me deal with the fallout.
Okay.
Okay. Okay. All right. So. See.
Okay, I think I will try to enter the grade tonight. I grade directly in where you are like submitting, like attach the home or like your work. So like if I'm not sure if you can see it, but like if you go there, you might be able to see it because I save it and you should be able to see it. But like I'm not sure if you like, if not, like I will manually enter the grade for each of you in like Blackboard.
Yeah, go ahead, do that, because what I'm gonna do in Blackboard, Sam, is I'm gonna compute the final grade as a weighted as like a sum of the individual grades.
Okay, so I guess Tariq and I will have to manually enter the grade into the grading center. Okay, fine.
I mean, if it's too much of a burden, just leave
No,
it.
no, that's fine. We wasn't sure how
Yeah.
like the grading system gonna work, and also yeah, like the other thing, I will email you.
Yeah, and I'll anxiously await those emails. All right, I'm gonna let you guys do the lab. I'll see everyone else on Wednesday.
Thank you, Professor.
Thank you.
Oh, blah. Hang on, let me have some email. Yeah, so the lab today, I think Tariq will like lead the lab today. I will help him with that, like, and he's kind of new, so don't buy him, I hope. And yeah, like the lab today is kind of short, but like you guys will have to do a lot of work in your own when you have to record the voltage of different combination of resistor, but the general idea should be really simple. So module 0, you will have to include one PDF with like the fill-in table for the resistor code and the number of components. In that PDF should be the fill-in table, as well as some images that is like of your voltmeter and like of your oscilloscope and the wave generator that you have to do like to generate a signal for section E and F. D and E, and then like in the attachment when you submit the homework, please include 2 video. One video is the stable LED where the LED is not blinking, is stable, and like the other one is like the blinking LED. So like and each of the video should be 10 seconds or less. And please pay attention to the LED blinking, because like if you set either the blinking speed too high or it is not compatible with your camera, you might or might not like see it blinking or completely off on your camera, even though like with your own eye, you can see it blinking. So just make sure to look over the video to make sure like you can see it blinking. I don't care about the frequency of the blinking actually. Just make sure that like I just want to make sure that you know how to use the wave generator to cycle out the sinusoidal signal with appropriate frequency. Yeah, that's all. Hope that answer your question. Like I just include that in the lab manual, and yeah.
Sammy, you ready to go?
Yeah. Like any more question for regarding module 0?
You can also ask in the Slack channel as well.
Oh yeah, like I just added all of you to the Slack channel for like the new channel for all the lab related question. So if you like any question, just like post your question over there, and other people may have a similar question as you, so we can answer it one and for all. I hope. Also, I have a meeting with my advisor tomorrow. So if you want to have an office hour, I think we may need to reschedule that. Just let me know on the Slack or email as well. And that's all for the logistics. Tariq, it's all your. I will be your observer.
Oh, wonderful. Okay. All right. So can everyone see my screen? Sam, can you see the screen as well?
Yeah. I'm seeing your screen.
Okay.
Yes, I can see it.
So with module 1, we are going to be looking at different types of circuits, that being in series, parallel, and then a combination of both. So we're not going to be going over the entire lab, but I'll guide you through the first experiment. So you set up your circuit, set up the 5-volt supply to the ADS, have a circuit with just the 1K ohm. I'll show you how that looks with the oscilloscope in a second. You need to initially record the initial voltage, which will be 5 volts, the current measured with the volts, and then what the calculated current is. You will be setting it up similarly to this circuit right here. Make sure that the oscilloscope channel is on, so that way you can pick up the readings. However, with the power supply, instead of connecting it over here, you'll be connecting it in this section right here. So how should the waveform app look? I believe you can see it here. You'll see that it's reading between 4 and 6, which means there's a 5-volt reading going through the oscilloscope. Make sure that your channel parameters are set to actually see these values. An offset of 0, so that it starts at a 0 value, and in a range of 2 volts. If you go any lower, you might not be able to see it. These parameters should be good because you're using a high level of voltage. And now to see what the voltage that's being recorded, you will go here to data, click on it, and you'll see that it's running through, and you just have to record that initial voltage right there at the time, the first second. And then for when you continue to experiment 1, you'll just replace that 1K volt with 10K volt, record the same data as you would for the first resistor, repeat it for the 47K resistor, and then you would move on to creating a series. Unfortunately, we can't show you how to do the series. You'll have to try it on your own. That would be your second experiment, moving on to your parallel, and then doing a combination of both. And that will be your module 4. And I think that's it.
Can I ask,
Sure.
can you show a picture of how they are connected in series and how they are connected in parallel? Just
Actually, we that's kind of similar to the your LED circuits. Like when you do like in the LED circuits, you have the LED circuits as well as the resistor, and those two components are in series. So if you did your home like your work on the previous lab, you should be able to do this. And the similar thing for the parallel resistor. So the way you connect the thing parallel is similar to how you attach the oscilloscope probe to measure the voltage across the across the resistor.
okay.
Also, if you're not too sure how to set up a parallel or series circuit on a breadboard, you can also Google it as well.
And also like try it now and let us know if you have any question.
Does anyone have any questions? Where do you write the 1K volt? So in the lab, in your lab, like Google Doc, you'll see that there is a table for each experiment. So for experiment 1, this is table 1. You would write in all the information here.
Quick question.
Yep. Go ahead.
So for the waveform, we're not using the WaveGen application, or are we?
No, for this lab, we are not using the wave generator.
So
Actually,
so that
actually you can use it using the DC light generator, but it's kind of overkill. So like just use the built-in 5-volt connector and it should work just fine. Actually, you can try to use the 12-volt as well, as long as like you fill in the table. You
Yep.
fill in the table accordingly. Yeah.
If you start with the 12 volt, make sure that you note down that you started with 12 volt and then work through the calculations with that value. Or else we're going to go ahead and assume that you started with the 5 volts and then your calculations came out weird.
okay. But our voltage that we're testing will always be at least the 5 volts unless stated specifically otherwise, correct?
Yeah.
Yeah. And also because this board doesn't have the current meter, so you will have to do the manual calculation. And I don't think Tariq show you that. Like Tariq, can you show them how to acquire the data like to the decimal? I think like yeah, okay.
Right here. Yeah. I show them to click data up here and then this table will appear.
Okay, that's good. You can do the calculation directly in the thing, but like you can look it up. It's kind of bothersome. I don't like it, so I don't show it. Yeah, to do well in this lab session, you will have to like, even though we don't ask you to submit the lab report right away, you still need to complete like the previous lab session, a module to be able to like proceed with like this lab module smoothly.
Can I have ask a question?
Sure, go ahead.
For experiment 1, it says, 1 second. When it says to measure the voltage drop, do we do this for the stereoscope? It's measuring the voltage drop during the first resistor and then the second resistor, right?
If I remember correctly, what I wrote, yes.
So do we use the 2 channels of the oscilloscope?
That's a really good observer. Yeah, I think you can do that. I think like that better than my imagination. Like actually, I would like when I was planning to do it, I would kind of planning to remove the prop. But like yes, exactly. You can use the 2 channel, and like that would be the same. It would use the same result.
Okay.
Did that answer your question? Yeah.
Yeah, it answered. And when you say the calculated, can you go to the table, please, too?
Sure, 1 second.
When you say I calculated, like just the V times, like using Ohm's law?
Yeah, you use Ohm's law to calculate like let's say you measure 12 volt and then you use 1K resistor, so like it should be 12 volt and like 12 something I think. But like the I you measure from the oscilloscope is there's a decimal after that, and I think you have to take into account the decimal. Just make sure that like you write up appropriately, and yeah, I think 2 or 3 number after the decimal should work just fine for us.
Okay. And Trey, can you run the oscilloscope application?
Sure.
Hmm?
I'll open it up in a second.
I just want to ask, how do you guys set it up? So I remember for last time we were changing the offset and the range.
No, like for this one I don't think we have to change the offset. We just have to change the range to make it like appropriate. So for example, in this window of Tariq, you can see like because we're measuring a 5 volt system. So like the range should be like for each of the division, it should be 2 volt to be able to show like the entire graph. And yeah, like and then you have to change the time as well, but for this circuit I don't think we have to bother with the time because the frequency is there's like it's a DC circuit and there's no like alternator voltage, so yeah, you don't have to show that because there's no frequency.
Okay, thank you. Thank you, Tariq.
Yeah.
I have a question.
Yep, go ahead.
For the lab report,
Hmm?
is there like a standard format? Like, do we have to do like intro
I just answer
discussion?
the question. Just answer all the question that we ask, and like that's it. You don't have to write anything. Like if
Oh, okay.
like if we want to know anything from you, we will ask the question directly.
So everything there is the actual report.
Yeah,
Okay,
like
that's what I was wondering.
yeah, but the thing is, for the lab report, like
Yeah.
I think in the email I sent out last week, I said
Yeah.
that like, we might add more question into like the lab manual after our session. So you might want to check back at this, at the latest 1 week after like your lab session for the
Mhm.
final question that we want to see you guys report include in the final PDF.
Mhm. Got it. And if we want to like send in like what we have so far, just so you can check off, we just email that to you, right?
Yeah, fair for me.
Got
Yep,
it.
that's good for me too.
Thank you.
You're welcome. Is there any more questions? because I can let you guys go early if there's nothing else.
Just a quick question on setting up the actual circuits. So for like experiment 1, it's just one resistor, and then the experiments following are just increasing the complexity of that simple circuit.
Yep. So with experiment 1, you're taking out the 1K ohm and replacing it with a 10K, and then getting those same. You're calculating the same values as well. That's just for experiment 1.
Okay. So we're just testing out how the different resistance levels affects voltage, and I calculated.
Yeah, and then like I just also want to make sure that you guys know how to use the breadboard correctly, and yeah.
Okay.
Because
Thank
like
you.
one is the building block for the next 2 lab module. Because if you don't know how to like build a breadboard using the parallel and series resistor, by the circuit component and power them accordingly and measure the voltage, you will have a lot of trouble in like the next 2 modules, because like it's like the complexity of the circuit increase exponentially. Actually, you will have to read the I'll do the introduction next week, no spoiler.
Well, that's comforting.
So there was a question asked today. We should be done with module 1. Ideally, if you can finish module 1 today and complete the graphs, answer questions.
Try out all the circuit combination and test is like test your calculated value, compare with your actual value, and see if it match your expectation. That means you have like you understand it, and the rest of the work was just like replacing the circuit with other component to measure the result. And yeah.
And all of the reports in one combined PDF won't be due to the last day of classes, so you guys have time to complete all the modules.
Yeah, actually, like for each of the module is one complete PDF. I don't want to receive like one PDF and then for all the image with no name whatsoever. So include everything in one PDF for each of the module. To do that, I think you can just copy the lab manual to your personal drive, and then like cut out the rest of the lab report, like lab manual, and just finish the first one, or you don't have to cut it out. It's up to you.
Quick question.
Go ahead.
So when we're sending in the lab report, are we sending all the modules in one PDF, or each module is its own PDF?
I think for now, I think each module is one PDF would be better.
Okay.
Yeah.
Did we discuss videos? Like I know like last week you're saying that the blinking light.
Like we discussed that at the beginning, but like what question do you have again?
Just like aside from the one PDF.
Yeah.
I'm just sending the videos apart from it, or try to incorporate in the
Like you will like when you submit the PDF for like the lab module, like this, I think you have 2 options: either attach the video into like the submission, or include that in like the session that Blackboard let you write your assignment, and then you include the video. I think that's option. If not, we will just scrap it. We're just testing it. I don't know how it works actually.
All right, thank you.
Yeah, like you guys can test it and let me know if that works for you. Like there's no penalty in some like in for early submission, so just go ahead and don't wait until the last minute.
Tariq, can you show on the wave gen application how you got to the graph again?
Sure. So you just over here, click data, and then the table will show up.
Okay, thank you.
Like if you connect your circuit like correctly, you just click run and the graph should show up like magic. But like if it's not showing up, either your circuit is not connected correctly, or like your parameter for the range is either too low or too high for the oscilloscope to show. So you just have to change the range like on your right hand side as Tariq is showing.
I think if you put the range at like 2, you should be able to see the voltage. Except if you use a higher resistor, you might need to drop that range a little bit.
Yep.
Also, make sure that the channel is on, or else you'll get weird numbers like I did initially. So make sure the channel switch is on.
One more thing.
Yeah.
Sorry.
Yep.
For the tables, we're putting the V that we got, like the voltage drop in those spots, correct? And then we're using those to calculate I, or how would we measure the I from V?
You're talking about
Yes,
this one right here?
One is you calculate the I using the voltage you measure from the oscilloscope. The other I is the absolute value, 12 volt. Like just say you got 12 volt, so just use 12 volt. But like for the other I measure from V, that means like you got like from 12 volt, you got 12.0.5 something. Just do the calculation using that value.
Okay, got it. So we're still doing calculations for both of them. It's just the I calculated is the theoretical one, and then I measured is the one that we get from.
Yes, yes. Like that will be the same thing for the following table as well. So yeah, that's good to clear that out of the way. And then you can calculate the error. Like there's many ways for you to calculate the error. Either way, like anyway, just fine for me.
What did you click to see the data? Okay, thank you.
Okay. think we're set to end it here if there's no more questions. You can always message us on Slack or email us if you have any questions about module 1. And there's the end of that. Sam, do you have anything to add?
I don't, but just look out for, I think I hope to finish my writing for module 2 by Saturday. So make sure just to go over that because like that module is kind of difficult. That's why it took me a bit of time to write before class. Yeah.
All right. Thank you guys.
And if there's no more question, bye.
Goodbye. Aisha.
I have one more question.
Yep.
I just want to know for the midterm exam, we had to do only 3 questions, not all 4, right?
Yes. Let me just remove Hedon. So I can just tell you what I was typing out. So we graded me and Sam graded all of the final questions of the midterm, but for some reason it doesn't show up on your side. It's usually where we do the homeworks. So we're gonna put in those grades throughout this week. From what I saw, from what Sam graded, you got a 13 out of 25 on question 13.
Oh,
Yeah. If you want to like discuss that question, you can email Yasik and talk him through how you solve that problem, and he's usually nice with giving back points or curving the overall midterm grade.
who is Yasik?
Professor Damaskowski.
Oh, okay.
So you'll see that grade up soon, sometime this week when we start putting them in the right location. And then you can speak to Professor Damaskowski
Okay.
at that time. All right.
All right. And one more question about the homeworks. About the homework number 2, I couldn't be able to submit because I sent him email. I sent email to professor that I had an exam back to back on the same day when the homework was due, and I forgot completely about the homework. I sent him email, but he did not reply. So do you want me to do it now and submit?
Yes. Can you also forward me that email as well that you sent to Professor Yasik as well?
Sure.
Yasik doesn't really, he's kind of bad at responding if you don't send him multiple emails.
Okay.
Don't tell him that. So if you send me that email that you sent to Professor Yasik and the homework as well, we'll know that you did it on time or a little bit later, and then we'll grade it and submit the grade as well.
Okay. All right.
Yeah. If you ever have a case like that again, send it to me and Sam because we're more likely to respond and make sure it's taken care of.
Okay. And one more question about module 0. So module, for example, if I don't understand anything, right? And can I send you that picture or anything like my question that I did not understand what I have to do here and there? And will you be able to tell me before like I submit my final report?
Yeah. One of the things, if you take a picture or tell us specifically which part of the module you're having trouble with, I'm pretty sure me and Sam will probably be able to help you.
Okay.
All right.
All right. Thank you.
Thank you. Have a nice evening.
You too.